Welcome to today's paper reading. Today's paper is titled Zero-Shot Tokenizer Transfer. This paper, titled Zero-Shot Tokenizer Transfer, is authored by Benjamin Minixhofer, Edoardo M. Ponti, and Ivan Vulić from the University of Cambridge and the University of Edinburgh. It is currently under review as a preprint. The paper introduces the concept of zero-shot tokenizer transfer, ZeTT, a new problem aimed at enhancing the flexibility of language models, LMs, by allowing the tokenizer to be swapped without performance degradation. The core challenge of ZeTT is to find appropriate embeddings for tokens in a new tokenizer's vocabulary. To address this, the authors propose training a hypernetwork that takes a tokenizer as input and predicts the corresponding embeddings. Empirical results show that this approach generalizes well to new tokenizers and maintains performance in cross-lingual and coding tasks while significantly reducing the length of the tokenized sequence. The paper also highlights that the remaining performance gap can be closed with continued training on a small number of tokens, and that the hypernetwork can be applied to fine-tuned LM variants without additional training. Language models, LMs, function by processing discrete tokens, necessitating a tokenizer to convert text into a sequence of tokens. Most modern LMs employ subword tokenizers, while others use byte-level or character-level tokenizers. A significant limitation is that once trained with a specific tokenizer, LMs cannot infer with a different tokenizer. This limitation has profound implications, particularly for non-English languages and specialized domains. To address these issues, the concept of zero-shot tokenizer transfer, ZeTT, is introduced. ZeTT aims to create an embedding matrix on the fly for any arbitrary tokenizer without prior data exposure. This is achieved through a hypernetwork trained on a diverse distribution of tokenizers, which predicts embedding parameters for any given tokenizer, preserving model performance with minimal additional data. Figure 1 illustrates how the hypernetwork predicts input and output embeddings based on the tokenizer. This approach allows the language model to use any arbitrary tokenizer without degrading performance. The hypernetwork is trained to predict the embedding parameters for any given tokenizer, enabling zero-shot tokenizer transfer. This method is applicable to various types of language models, including encoder, decoder, and encoder-decoder models, making it a versatile solution for detaching language models from their original tokenizers. In this section, we discuss the fundamental components of tokenizers and embeddings. Tokenizers function as a mapping from text to a sequence of elements in a vocabulary. Specifically, a tokenizer is defined by a tuple VT, where V is the vocabulary and T is the tokenization function. Importantly, the vocabulary and the tokenization function are distinct, meaning there are multiple ways to encode text as a sequence of tokens within a given vocabulary. After tokenization, the model represents the sequence of tokens through an embedding function E, which maps tokens to a model-dimensional vector. These embeddings are utilized both at the input and output stages of the language model. Embedding parameters may or may not be shared between the input and output stages. Contemporary language models often employ subword tokenizers, such as BP or Unigram LM, which offer efficiency and open vocabulary capabilities. However, subword tokenization presents challenges, particularly with sequences of numbers and text containing spelling errors. The methodology focuses on training a hypernetwork to find parameters theta that map tokenizers to embedding parameters for a pre-trained language model. The training objective is to minimize a loss function L theta, which substitutes the original embedding parameters with predictions from the hypernetwork and uses a different tokenizer. To achieve this, texts are sampled uniformly from the training corpus, and a procedure is introduced to sample diverse Unigram LM tokenizers, ensuring high variance to encourage generalization. Additionally, a warm-up stage is included where the hypernetwork mimics the original embedding parameters, followed by an auxiliary loss to prevent drift from the warm-up stage. This auxiliary loss is combined with the main loss to form the final training objective. Figure 2 illustrates the process by which the hypernetwork, composed of a language model HLM theta, learns to combine embeddings under the original tokenization to form a new embedding. This process also amortizes over the tokenization function. The figure shows how each token is decomposed using the original tokenizer TA, embedded with the original embedding ZA, and then passed through multiple transformer layers to form the new embeddings B. This method ensures that the hypernetwork can produce a single embedding suitable for a wide variety of different tokenization functions. Table 1 presents the accuracy results on the XNLI dataset when adapters trained for the original XLMR model are reused with new zero-shot transferred language-specific tokenizers. The table highlights the absolute change in accuracy from applying our hypernetwork, and the average decrease in token length of the language-specific tokenizers compared to the original tokenizer. The accuracy changes observed range from a decrease of 3% to an improvement of 1%, with an average decrease in token length of 14%. This reduction in token length translates to an inference speed increase of more than 16%. Table 2 presents the performance metrics of Mistral 7BV0.1 after undergoing zero-shot and n-shot tokenizer transfer processes. The evaluation focuses on the transfer to the GPT-2 tokenizer for natural language benchmarks and to the StarCoder tokenizer for human eval-pack. Notably, the table highlights that continued training with the original tokenizer does not consistently enhance performance. The data underscores the effectiveness of the transfer methods in adapting the model to new tokenizers while maintaining or improving its performance across various benchmarks. In this section, we discuss the data sources used for training, the evaluation benchmarks employed, and the models and tokenizers involved. For data, we utilize the English subset of the MATLAB 400 corpus and code from the StarCoder data, with a sampling ratio of 7:3 for English to code. The evaluation benchmarks include PyQA, HeliSwag, BoolQ, MLU, ARC, and Human eval-pack for English, and XNLI, Scopa, and MLU for multilingual evaluation. The models evaluated include Mistral 7B, XLMR, and TinyLlama 1.1b, with tokenizers such as GPT-2 and StarCoder, and language-specific monolingual tokenizers trained with SentencePiece. Table 3 presents the accuracy of Mistral 7B on the Scopa benchmark using language-specific tokenizers transferred via Focus and our hypernetwork. The table shows the accuracy for each language, comparing the original tokenizer, Focus, and our hypernetwork. The standard errors for the accuracies are between 2.1% and 2.3%. The average accuracy across all languages is 54.6% for the original tokenizer, 52.3% for Focus, and 57.1% for our hypernetwork. Table 4 presents the 5-shot accuracy of Mistral 7B on the multilingual MLU benchmark using 3 different tokenizers, the original, one transferred via Focus, and another via the hypernetwork. The data shows varying accuracy across languages such as German, Spanish, French, Italian, and Russian. The original tokenizer maintains higher accuracy compared to the Focus and hypernetwork transferred tokenizers, indicating a potential gap that could be addressed through continued training. Table 5 presents the single model rating results on MTBench for transferring Mistral 7B Instruct v0.1 to the GPT-2 tokenizer using a hypernetwork trained for the base Mistral 7B model. The evaluation is conducted using GPT 3.5 Turbo 1106 as the judge. The table compares the original fine-tuned model, originally, with the base model, which uses the same tokenizer but substitutes the embeddings for those of the base model. The lambda parameter represents the scaling factor applied to the weight differences in task arithmetic, as described by Ilharco et al., 2023. The results indicate the performance of the model under different embedding and lambda conditions, providing insights into the effectiveness of the transfer process and the impact of embedding substitutions and scaling factors on model performance. Table 6 illustrates the probability of pre-tokens being tokenized equivalently after conversion to byte level, or unigram LM. It shows that the probability of preservation is high across different models, ranging from 99.4% to 100%. The bits per character for the original tokenizers vary from 0.675 to 0.930, indicating the efficiency of tokenization. For byte-level conversion, the addition of extra tokens ranges from 0 to 522, which is not measurable in terms of bits per character due to the lack of corresponding embeddings. Table 7 presents the bits per character (BPC) for GPT-2 using its original tokenizer and two alternative tokenization methods, unigrammified and unigram-LM with substring frequency scores. The original GPT-2 tokenizer achieves 0.930 BPC, while the unigrammified version slightly decreases to 0.920 BPC. The unigram-LM method, however, shows an increase to 0.964 BPC. This comparison highlights the impact of different tokenization strategies on the efficiency of GPT-2's token representation. In this discussion, we explore the conversion of tokenizers to byte-level and unigram-LM. For byte-level conversion, the goal is to ensure that token decomposition is always possible. This is straightforward except for BP, where the atomic units for merges need to be changed from characters to bytes. The success of this conversion is measured by the probability that a pre-token results in the same token sequence in both the original and converted tokenizer. For unigram-LM conversion, we introduce a process called unigrammifying, which checks if a diverse distribution of tokenizers is possible. The results show minimal performance degradation when substituting the original tokenizer with a unigram-LM tokenizer. Additionally, we analyzed the hypernetwork, finding that the predicted embeddings are robust to the choice of tokenization function. This robustness calls into question prior work on embedding transfer across tokenizers. Finally, we estimate the computational overhead of the hypernetwork, observing a 12% overhead from applying the hypernet. Table 8 presents the parameter count and flops estimates for the hypernetwork and its corresponding main model across various setups. The data highlights that the computational cost is relatively lower compared to the parameter count, primarily because the setup avoids the embedding, which significantly increases flops. This analysis is crucial for understanding the efficiency and performance trade-offs in hypernetwork configurations. In this study, the authors have successfully established zero-shot tokenizer transfer (ZeTT), a method that allows language models to be transferred to a new tokenizer without the need for any training. They found that while prior heuristics for embedding initialization provide a basic baseline, they often fall short. To address this, the authors introduced a hypernetwork-based approach, which significantly improves the baseline and can be further enhanced by continued training on a small number of tokens. This approach preserves the embedding space of the original model, enabling applications such as reusing adapters trained for the original model with a different tokenizer, and transferring fine-tuned models to a new tokenizer using a hypernetwork trained for the base model. Overall, this work represents a significant advancement in making language models more flexible and reusable by detaching them from their original tokenizers. Thank you for watching.